So today we're going to talk about a couple of different forms of heat. Now, the first type is what we call heat of phase change. And essentially, this is when a substance that changes from one phase to another, right? In order for that to happen, heat is either going to be gained or lost, right? So, first example, delta H of fusion. So fusion, it refers to going between solid and liquid. Okay, so when we say heat of fusion heat of fusion, that means you're talking the amount of energy that needs to either melt 1 mole of ice or freeze 1 mole of ice. The amount is the same. Whether it is melting or freezing depends on what you are doing. Are you adding energy or are you removing energy? Right? So is the sign positive or is the sign negative? Okay. So another term is the heat of vaporization. So vaporization is referring to the amount of energy needed to go from the liquid state to the gas and vice versa. So are you vaporizing it or are you condensing it, right? Condensing, going from gas to liquid. So in the case of going from gas to liquid, in order to do that, actually let's just write out an equation. Liquid goes to gas, the delta H will be positive, because it's going to require energy to do that. So you can think of heat in that case as a reactant. Whereas if you were to do the opposite, go from gas to liquid, this would release heat, and so delta H would be negative in this case. And I can make the same equations for above. When we're talking about heat of fusion, if we go from solid to liquid, you're talking about melting. So is energy required or released to melt something? It's required. So heat would be a reactant in that instance. And so the delta H for a process like that would be positive, right? Whereas if you were going from liquid to solid, energy would be released because all the particles are slowing down. So heat is a product. The delta H in that instance would be exothermic. All right, are we okay with those equations? That makes sense? The sign conventions? Okay. All right, so the heat of fusion and the heat of vaporization is going to be different for all substances, of course, right? So in the case of water, the value for heat of fusion is 6 kilojoules per mole. So let's start with this simple example. Find the amount of energy needed to melt 1 gram of ice. If I have 1 gram of ice, well, I really have 1 gram of water, right? And so because the heat of fusion, heat of vaporization is in terms of per mole, I need to convert to moles. So mole water is 18.02 grams, so 1 divided by the molar mass. So 0.055 moles of water is what we are talking about. And if I'm trying to melt it, I'm going to use the heat of fusion, which is 6 kilojoules per mole. Where did that number come from? Right here. So if I have 1 gram it's going to require 0.333 kilojoules, or 330 joules. So as long as you know the mass of ice that you have, you guys know how much energy it's going to take to melt it. Okay, that's the value you use, heat of fusion. Okay, it's a fixed value. If we were to flip this around, and if I were to give you mass of water and ask how much energy does it take to freeze this, you're using the same value. It's still 6 kilojoules per mole. The only difference is the energy value, the sign is the opposite, right? But the calculation is the same. Okay? All right, so let's talk about then a multi-step problem. Oh, by the way, I need to mention that this is very important. During phase change, right, like we're talking about here, when you're changing from either a liquid to a solid or solid to a liquid or gas to liquid, whatever, as long as the phases are changing, temperature is constant. Very important. During any phase change, like during the process of melting, that ice, once it gets down to the melting point, which is 0 degrees, it stays at 0 during the entire melting process. And the temperature does not change until all of the ice has been converted. Once the last little bit of solid ice has been converted to liquid, then the temperature may increase. Okay, so simple example. You go to a restaurant, you order, and they give you a glass of ice water. Right? If I see ice cubes in that water, I know the temperature of that water is 0, as long as I see the ice cubes. Right? Now, there's heat in the air. There's heat all around. There's heat in your hand. And as time goes on, the ice cubes in that cup of water get smaller and smaller and smaller. Eventually, you know all the ice in that glass is going to melt, right? And it's only after that point, when all of the ice has melted, then the temperature can start to increase. Okay? So that's just something important to know. And we'll talk about exactly why later on, okay? We'll get into more detail later. But for now, just know that during a phase change, the temperature is constant. Okay, let's try another example. Find the amount of energy needed to melt. This time I got 15 grams of ice. And it says, and then warm it up to 20 degrees. So there's two things happening. The first part is melting. The second part is warming. Okay, so I'm actually going to need to find the sum of two calculations. The melting part, well, that's fusion, and I just showed you how to do that. We've got 15 grams. We need to convert it to moles. Okay, so 15.0 divided by 18.02. All right, so we're talking about 0.832 4. I'm going to carry an extra sig fig for now. We'll round it later. Okay, that's how many moles of water I'm talking about. And the heat of fusion is 6 kilojoules or 6,000 joules per mole. And 4994 joules. Okay, that's how much energy it takes to melt. But now that it is melted, so essentially what has happened is this. Here's my ice cube. It's 15 grams. I've just melted it, now it's a puddle, right? The temperature at which the melting process takes place is the melting point. And the melting point of water is 0 degrees. Once that water is, or once the ice cube is all melted, that water is 0 degrees because of what I mentioned earlier. During phase change, temperature does not change. But now that it is completely melted, temperature will increase. And so now we're describing a situation where we go from liquid at 0 to liquid to 20. So if you remember from last week, there's an equation which allows us to calculate how much energy is needed when there's a change in temperature involved. What equation am I talking about? Yeah, Q equals MC delta T, right. So if we were to color code this value here represents this process right here, okay? And now we're going to calculate the energy that needed to warm it up. So the heat flow equation is used when temperatures change. So that would be appropriate here. So let's go ahead and see what values we have. All right, so the mass, do we have a massal of our water sample? Of course we do. All right, it's 15 grams. The specific heat of water is a fixed constant, 4.18 joules per gram degree Celsius. And the temperature, do we know the temperature change of this water sample? T final minus T initial? Yeah, 20 minus 0, right? Or 20 degrees. Okay, so let's run the numbers. Oops. Okay, so we had two processes. We had the melting process and then we had the warming process, each of which had to be calculated independently, but now we can answer the overall question. How much energy was needed to do this whole process? Well, now we just take the sum of the energies that we calculated, right? So E total is equal to 4994 plus 1254. So 6248 joules. I'm kind of sloppy with the temperatures I gave you. We'll just call this 6200 joules. Okay. The point of this question is for you to recognize that when heat is absorbed, a substance may change state, or it may change temperature, or both may happen. And you need to know how to approach the calculation when that happens. If I said to you, here I've got a beaker of water, it starts at 20 degrees, and I heat it up until it gets to 70 degrees. The only thing that has happened was a change in temperature. And so therefore, the only calculation you would carry out in that scenario would be this, right? But if there is a change of state involved, you have to include either heat of fusion or heat of vaporization. Now, clearly these values here of 6 and 40, these are relative to water only. If there was another substance, like the heat of fusion for aluminum, for example, well, those altogether would be different values, of course. And you would not be expected to know those. Those would be provided to you in the context of the problem. Okay? Okay. Just to give you one more example of that, I'm going to insert a page here. We're going to try another problem. Okay. So the specific heat of ice is 2.09 joules per gram degree Celsius. So you might think, why am I giving you the specific heat of ice? Don't we already know the specific heat of water? Yes, you know the specific heat of liquid water. This is solid water, and thus it carries different specific heat. Okay? So here are these two values. Okay? So let's say that you're on an Arctic cruise. All right? And you guys hit a glacier. Okay? And let's say the boat doesn't sink. You just hit a glacier, but you decide to hop out. You hop out. And you want to recover a chunk of Arctic ice in the name of science. Okay, so you got this chunk of Arctic ice, and this Arctic ice, it has an initial temperature of -3 degrees Celsius, because you're in the Arctic after all. So you decide to bring it into your cabin. You go back aboard your ship, you go into your cabin, and so this ice, and let's say we have a kilogram, all right? 1 kilogram. or 1,000 grams, which starts at -3 degrees. You bring this into your cabin, and it just sits there in your tub in your suite. And because your cabin is not, the thermostat is not set at -3 degrees, what's going to happen? What's going to happen before it melts? It has to warm up first, because what is the melting point of ice? 0. What temperature is it now? Yeah, you gotta warm it up. Okay, so there's a process to bring it from -3 degrees to 0 degrees. And then once it's at 0 degrees, your cabin temperature is still warmer than that. So it's going to melt and turn into water. And then after it has melted and turned into water, it's going to reach thermal equilibrium with the air temperature in the room. What's a reasonable temperature in a room? 20 degrees. So this is the thermal change that this kilogram of Arctic ice is going to go through. Let's calculate how much energy is needed to do this. All right, so let's number the steps first. 1, 2, 3. There's 3 calculations we have to carry out. So for calculation 1, what is the approach? Are we using heat of fusion, or are we using Q equals MC delta T, and why?
We're using Q equals MC delta T.
Why?
Because we're warming up the ice.
Okay.
And the phase does not change.
Phase does not change, but temperature does. So in calculation 1, okay, so what do we know? We know the mass is 1,000 grams. We know the specific heat of ice, not liquid, right? Of ice, 2.09. And the change in temperature, final temperature, 0 minus the initial temperature, 3. So 0 minus a -3. Okay. So we're talking about 6,270 joules for that first calculation. All right, so now the chunk of ice is at the melting point. So when something's at the melting point and it's absorbing heat, it's going to melt. So we're using heat of fusion. But remember, in order to use heat of fusion, you have to convert what you have into moles. All right, 332,963 joules. Which, if you look at it, it sounds like a big number, but look what you're doing. You're multiplying 1,000 by 6,000, then you're dividing by 18. So it follows. All right, and the last step, we're taking this liquid water at 0 degrees, and we're changing its temperature to 20 degrees. Okay, so again, the mass is 1,000 grams, but now we need the specific heat of liquid water. And our temperature is final minus initial, so 20 minus 0, so 20. All right. Okay. So the total amount of energy needed to do this, I just kind of add these all up. But we can probably only really call this, we'll go with We'll go with that. 423 kilojoules. Once you start dealing with numbers and the thousands, you should switch to kilo. All right, this goes for grams, joules, whatever unit you're using. All right, how are we doing on that? You guys, you're all good? What if this were the opposite process, guys? If I took water and I froze it first, right? And then I got it down to -3, it would be the same calculation, but your signs would be different, right? Okay. All right, good. So that's how we use heat of fusion. If I were to use heat of vaporization, that would be if I'm vaporizing, going from liquid to gas, like, you know, like water to steam or vice versa. Okay, but the how you do the problem is the same. Okay. So then, now if you're okay with heat of fusion, let's talk about enthalpy. And this is a weird one, right? Now we're actually kind of scraping the surface of thermodynamics. And thermodynamics we're going to cover a little bit in this unit as far as it pertains to heat, but the real thermodynamics unit is at the end of the year. So I'm going to give you enough to relate to what we've been doing, right? And so this unit is called calorimetry or thermochemistry, so we're dealing primarily just with heat because there's other factors involved with thermodynamics, but we'll deal with them later. All right, so the term enthalpy is the energy potential in a system. The energy potential. Some systems have more potential energy than others. A stick of dynamite has more potential than a plastic tube, right? So it all has to do with the chemicals that are involved. The symbol we use for enthalpy is H. So that delta H that you saw earlier that I referred to as heat of fusion, technically it's called enthalpy of fusion and enthalpy of vaporization. All right, so the H means enthalpy. I called it heat because you didn't know what that meant back then, but now you do. Okay, so the thing about enthalpy is that it cannot be measured directly. So in a practical sense, any calculation we're going to be carrying out in terms of the context of a change in enthalpy, delta H. Okay, so that's primarily what we'll be calculating. Enthalpy is what is called a state property, and a state property is a property that depends only on the present state of the system. It doesn't matter how it got there. Okay, so another way I think of this is if you're a business owner and you need to make a profit, so you could be a business owner and you could sell lemonade on the corner of your street. Okay, you could spend $10 in materials and you can earn $40 gross. So how much did you profit? 30, right? You put in 10, you got 40. What the difference is 30, right? Okay. Profit is a state property. I could be a multi-million-dollar, tech company, and I could spend $1 million, and my earnings, our gross earnings that year could be $1 million and $1,030. Well, $1,030,000 minus $1 million is $30. I could have profited $30. It doesn't matter how you achieved the value. It just matters what the value is. Okay, another example. I'm in this room right now. I'm sitting on this stool right now. I could have gotten here several different ways. I could have walked in from the parking lot, up the stairs, through the cafeteria, through the math science stairwell, and walked straight here. Or I could have run around the building 3 times, went up through foreign language, then came around by the library, and then here. But the point is I'm here. Both of those processes would have gotten me here. The fact that I'm here means this is a state property. Do you guys understand the difference? Okay, state property, all depends on what the current state is. Doesn't matter how you got there. Okay. Other state properties. Temperature. What's temperature in this room? Right now, it's probably about 20 or 18, 19 degrees, 18 and a half degrees. Okay, well, what if, to get this room to 18 and a half degrees, what if we got it up to 60 degrees Celsius first and then cooled it down? Or what if we got it to negative 5 degrees Celsius and then warmed it up? The point of the matter is that right now it is 18 and a half degrees in here. Okay? All right. Things that are not state properties. Heat flow is not a state property, because in order to get the temperature of this room to this temperature right now, you could have done either one of those two scenarios that I mentioned, one of which would waste more heat than the other, right? So how much money you put in to your business, right, and how much you get out of it, those are not state properties. The state property is your profit. Okay, but different companies can spend more and make more, but at the end of the day, what really matters is the profit. Work is not a state property, because you can do far more work in some scenarios, right? Not everybody studies the same amount of time for a test, right? So to achieve the same results, two people who score the exact same score on a test, one person might have studied for 10 hours, one person might have studied for half an hour. Okay? Are you guys getting the idea? State property versus non-state property? Okay. All right. Not to belabor it, right? It's you just need to understand what it is generally, but that's kind of all we're going to apply there as far as that. All right. So, if a process takes place at constant pressure, like say a chemical reaction takes place at constant pressure, which, by the way, where do we do our labs? In the lab. In the lab, where the air pressure, do I manipulate the air pressure in that lab in any way? No. So every lab you do is carried out under constant pressure. Okay? The majority of the processes and study that we do takes place under constant pressure. So the only work done is pressure volume work. What that means is we can account for heat flow by measuring the enthalpy of the system. All right, that probably doesn't make any sense. Let's break it down. So enthalpy, remember the symbol's H. Enthalpy is the potential energy in a system. And mathematically, it is the internal energy, which you guys know as E, plus the product of pressure and volume. Okay? Pressure and volume. When the system changes at constant pressure, which it does for us in a chemistry lab, the change in enthalpy is calculated to be the change in the energy plus the pressure volume product, which, redistributing to simplify, becomes this. So delta E, the change in internal energy, will happen because of heat and work. Remember this? The first day we said how much work is this doing? How much heat is there, right? So this is the substitution for delta E. And P times delta V is otherwise known as work. Right? But because the sign is negative, because a system that does work loses energy. Right? So the negative. So if we substitute these in, so in goes Q plus W for delta E, it becomes this. All right? Negative P times delta V is work. So P delta, the V dropped out here. There should be a V here. Anyways, it's substituted in. What we get is delta H is equal to Q plus W minus W. Or in other words, the change in enthalpy is equal to the heat flow at constant pressure. And this greatly simplifies our calculations. And this is all due to the benefit of working under these conditions where the pressure does not change. Believe me, this is a vast simplification, but it is completely practical and valid for what we are doing. Now, This can change in scenarios where you have to carry out reactions in like a hyperbaric chamber, for example, a chamber in which the pressure is adjustable, right? And some reactions will need to be carried out that way, but nothing that we do, right? That's more like, higher end stuff, graduate level college work. All right, all of that was meant to just simplify this statement right here. Okay, that means we can equate the change in enthalpy with heat flow. That's kind of the point. So, why did I bring that up? Why even go through all of that? Well, because we want to take the empirical data from a lab experiment and allow us to find the enthalpy of reactions. So, one of the simplest labs for calculating this is enthalpy of solution, and this is actually our next lab that we'll be doing tomorrow. So, the enthalpy of solution is simply the change in enthalpy, delta H, when a substance dissolves. It's typically performed in a coffee cup calorimeter. And coffee cup calorimeter means like a styrofoam cup one, like the ones we have. You know how they're styrofoam and there's like literally a coffee cup in there? Okay, that's all it means. So, we can't take the temperature of the chemical itself. Like you can't just jab a temperature probe in like a pile of salt, right? It's not really going to be accurate. So what we need to do is measure the temperature and calculate the Q of water first. So let's talk about calcium chloride. You guys should be able to recognize this as a dissolving equation. It's an ionic solid, and as it dissolves, it ionizes. You got calcium ions, you got chloride ions. Okay? So let's say that in doing this, the temperature of the water increases by 86 degrees. Let's calculate the Q of the solution using the total mass. Okay, so let's take stock of everything they just mentioned. 10 grams calcium chloride into calorimeter. We had 20 grams of water. Right, the T initial and the T final. It says the change by 80 degrees, so actually, I guess that's irrelevant. The point is the delta T was 86 degrees. Okay, and the specific heat of water, 4.18. Now, I will say in a situation like this, when we're making a solution, the C of the solution is approximate to the specific heat of the water. So if we know the specific heat of the water being 4.18, the specific heat of the solution is going to be 4.18 because the vast, vast majority of the mass of the solution is the solvent. It's primarily water. I had 10 grams. Okay, well, maybe here it's not that different, but we're just going to make that assumption. You can make that assumption for all our calculations. Normally, we'd be using more than 20 grams of water. Okay, so the thing about the solutions is that your solution mass is equal to total mass, which means 10 grams plus 30 grams. Oops, no, 10 grams plus 20 grams. All right, let's calculate this. Q of solution. What is the mass of the solution? 30 grams. What did we say the approximate specific heat of solution is? Same as water. What is our temperature change? It's 86 degrees. Okay. So 30 times 4.18 times 86. Okay, so we get 10784 joules. Okay. Are you guys okay with those calculations? All right, some points we need to stress. Solution mass is equal to total mass, so that means in your lab, when you're using the mass value, make sure that you add the solvent and solute mass together. The specific heat you're using is going to be approximate to that of water, so just use that value. And you'll be able to measure temperature changes because you'll have a temperature probe, so you know what the temperature was before and after the mixing. Okay? So now the question is, calculate the Q of the reaction. Reaction. Meaning, this is the reaction right here. Okay? What you calculated here was Q of the solution, or more specifically, the Q in, I should say the Q of surroundings, because technically that's what it is. Why am I calling it Q of surroundings? Is because what is actually reacting? It's the chemicals themselves, right? So Q of the calorimeter and Q of solution mean the same thing, because that's what's taking place with the water part of the reaction. So when they say Q cal is equal but opposite to Q reaction, that's because whatever energy change that's happening is going to be opposite of the value of what's taking place in the reaction. So what that means is Q of reaction is equal to negative 10,784 joules. The chemicals had to release the energy in order for the water to go up in temperature. Okay? All right. So, to calculate delta H of reaction, because we know that delta H and Q are equal, as we just established, because this is taking place in lab where the pressure is constant, then this assumption is made. But the only difference is we express delta H of reaction in specific units, kilojoules per mole. So, kilojoules per mole of reactant. Well, I need to figure out how many moles of reactants I have. I have the joules. I can turn that to kilojoules, no problem. Right? This would be negative 10.784 kilojoules. But I need to find my moles. So now I look and see, all right, how much of the solute, how much of the reactant was used? 10 grams. 10 grams of calcium chloride. All right, the molar mass of calcium chloride is like 110 grams. So 0.0909 moles. So now that I have the kilojoules and I have the moles, delta H reaction is equal to negative 118 kilojoules per mole. This is an exothermic reaction. When I dissolve calcium chloride, I expect the temperature overall inside the calorimeter to increase. Because energy is being released from the actual chemicals, it's going towards the water, which is what you're actually taking the temperature of. This is how we calculate heat of solution. Now, what one simple step is going to mess up your sign if you forget it? Believe it or not, this is the most common mistake right here. Once you calculate the Q of what's in the calorimeter, you have to remember the sign is going to be opposite that for the reaction. Okay? So you just flip it. And then you convert your solute into moles. And then you take your joules, turn it to kilojoules, so kilojoules divided by moles. And there's your answer. Okay. So, if you're good with that, let's go ahead and have you try this example on your own and see what you get. And I'm going to go ahead and stop the recording here.